Hey guys, welcome back to lecture series on linear differential equation with a constant coefficient, which is from M3 subject. So in our today's video, we are going to understand some of the example. We are going to solve some of the example which are based on the Cauchy homogeneous linear differential equation. So about the theory and the topic I explained in my previous lecture. So if you are interested to see this video, check in my playlist, or you will get here at the up there and on I button. Okay, yes. So let's start some of the example which are most important for your upcoming SPPU exam. Okay, so let me write example here. So here is the example. Okay, x cube d cube y by dx cube plus 2x square d square y by dx square plus 2y, which is equal to 10 into 1 plus x plus 1 by x. Okay, so we have to find out the complementary function and particular integral. That means complete solution for this example. Okay, let's get start solution over here. Okay, so as we have given a differential equation, it is in the form of a Cauchy homogeneous linear differential equation. Okay, so what we have here, given differential equation is in the form of linear differential equation. Okay, linear differential equation, given linear differential equation in the form of Cauchy homogeneous linear differential equation. Okay, Cauchy homogeneous linear differential equation. Okay, now see that how one can identify as we have Cauchy homogeneous linear differential equation. Now it is way easier to find out whether it is a Cauchy homogeneous linear differential equation or not. Okay, now see that along with the differentiation you will get the term of that dependent variable. Okay, independent variable and its constant. So as we have x is an independent variable, we got that x over here, that constant it is also here. So if we get to x square such a constant independent variable, okay, then we consider this one as a Cauchy homogeneous linear differential equation. So for finding the solution of these equations, we go for some substitution that we learn in our previous video lecture. Okay, yes. So in such a case, as we have x cube, that we don't want it here. Okay, x cube to x square, these terms are going to make us a trouble. Okay, for finding their solution. So what we do, we are going to remove that x cube to x square. It's just not that easy to remove. We have to substitute some of the values. Okay, so we know that we go for the substitution. What substitution we learn in our previous lecture? Substitute. Okay, what is we are substituting here? X, which is equal to e to the power z. Okay, this one is the value that we are substituting here. It is not only for x which is equal to e to the power z, we apply log to the both sides, so we get the value for z also. So why I am applying here, I will explain later on. Just first of all understand the method. Okay, so I will explain to you all why we are taking these values. Okay, then we write log of x which is equal to z. Okay, log of x which is equal to z. Okay, and d by dz. Okay, d by dz we take it as the capital D here. Okay, yes. So log x is a z, then we write a dz by dx. What we will get, the dz by dx? I am differentiating that log x which is equal to z further. Okay, so differentiation of a z with respect to x, okay, which is equal to log x having differentiation 1 upon x. Okay, so these are the three values we have here. Okay, using these three values we are going to solve this one. Okay, we have to substitute this one here, but it's not that direct substitution. So we take their substitution with along with their differentiation. Okay, yes, that means whenever we have x into dy by dx, okay, whenever we have x into dy by dx, we write d by dx as a capital D. Okay, that means we write dy. X into dy by dx can be written as dy. Okay, again these are the value I explained in my previous lecture how they are coming. Okay, so if you don't know how these values are there, okay, check in my previous video. Okay, I explained there in that video. Okay, so x into dy by dx can we write capital D into y. Again, x square into d square y by dx square. We write d square, okay, we write as we have x square into d square y by dx square. So you can take d square or you can take d into bracket d minus 1, okay, that means d square minus d, it is there, okay. So d into d minus 1 into y, okay. So that one I explained in my previous lecture, what is the logic behind of this, okay. So if you are confusing to understand these values, go and check in my playlist, okay. Yes, so x square d square y by dx square, we write d into d minus 1 into of y, okay. Again, so when we have cube, that means third order differentiation also, x cube d cube y by dx cube, okay. X cube d cube y by dx cube, we just extend the one value here, d into d minus 1 into d minus 2 into y, okay. So we write d into d minus 1 into d minus 2 into y are the these are the value that we are going to replace here in our Cauchy's homogeneous linear differential equation, okay. Yes, so we are going to replace all these values over here. Even also we are going to replace x here, okay. So let's go for the replacing all these values, okay. So x cube d cube y by dx cube, okay, into d minus 1 into d minus 2 into y, okay. This is the value for that differentiation, okay. So x cube d cube y by dx cube, replace it here. So I'm going to write this one as d into d minus 1 into d minus 2, okay. This is the value that I'm going to replace here, okay, plus. So x square d square y by dx square, what is the value for x square d square y by dx square, okay. So I'm not taking y here, okay, I'm taking directly y out of the bracket outside here, okay, because I'm skipping one step, it is easier to understand, that's why, okay. So x square d square y by dx square, okay, we write d into d minus 1, d into d minus 1, but it is not only d into d minus 1, as we have to multiply here. So 2 into x square d square y by dx, so that means 2 into d square x y by dx square is equal to 2 into d minus 1, okay. So 2 we have to add here, okay. Yes, 2d into d minus 1, okay, plus 2y, we cannot change anything here, as a y we free from differentiation, okay. So we write a 2y which is equal to 10, okay, 10. Now see that as we are replacing all the x variable, x differentiation with respect to that x independent variable, so we have to replace that x also, okay. We are going to replace that x here. So to replace x, just see this one here, x which is equal to e to the power z. So put this value here also in instead of x, okay. So x plus 1 by x can be written as e raised to z plus 1 upon e raised to z, okay. Yes, so we are going to write e raised to z plus 1 upon e raised to z. I replace all these values over here, okay. Now what do? We are going for simplified step, okay, simplified step for this one. So as y taken common from everywhere, it is here, okay. So y it is outside. Yes, let's go for finding their multiplication and everything here, so we can easily find out the roots over here, okay, for our auxiliary equation. Okay, so what we write here, d square minus d, okay. So go for solving, it is easier, but still I will explain, okay. D square minus d which multiplied by d minus 2, okay, plus 2d square minus 2d plus 2, okay, into y which is equal to 10 into e raised to z plus 1 upon e raised to z, okay. Okay, so keep that term as it is, just we want the simplified form of these two terms, okay. Yes, so what we do, go for the multiplication of these two brackets. So this into this, this into this, this into this, and this into this, okay. D square into d, we write d cube, okay. D square into d, we write d cube. D square into minus 2, we write minus 2d square. Minus d into d, minus d square. Minus d into minus 2, we write a plus 2d, okay. That minus get to the positive, okay. Yes, plus 2d square, keep as it is, minus 2d plus 2 into y which is equal to 10 into e raised to z plus 1 upon e raised to z, okay. So we are not going to change anything here, okay. So I am just trying to simplify this step further. Yes, so what we have, see that similar term, take it together, try to cancel them. So we don't have the term of a d cube here, so keep that d cube as it is, okay. Keep that d cube as it is. Minus 2d square cancel with the plus 2d square, Okay, plus 2d cancel with a minus 2d. After that d cube we have minus d square. Okay, minus d square plus 2 into y, which is equal to 10 into e raised to z plus 1 upon e raised to z over here. Okay, now see that I reduce our given Cauchy homogeneous linear differential equation. Okay, this one is our Cauchy homogeneous linear differential equation. I reduce this one into the linear differential equation with a constant coefficient. Okay, I reduce this one here with a linear differential equation with a constant coefficient. Now later on, for finding the particular integral and complementary function, it is as same as our previous example. I explained everything, how to find out the particular integral and complementary function, that we have to follow it further. The important part, it is only to find out this process. Okay, this one is the entire process. I hope you all have understood this process. Now later on part, it is easier for finding the complementary function. Okay, for finding the complementary function, we have to find out the root of this cubic equation. Okay, let's go for finding complementary function now. Okay, complementary function. So first of all, finding the complementary function, we write auxiliary equation. Okay, so auxiliary equation, which is a d cube minus d square plus 2, which is equal to 0. Okay, so for finding the roots of this auxiliary equation, directly it is not that possible. Okay, we have cubic form. First term is a cubic, that means we have 3 roots over here. Okay, this one is a 3. So for finding the roots of this cubic equation, we have to apply synthetic division. Okay, as already I explained how to find out the factors. Okay, so we can see that here, if we go for adding, there's alternating coefficient. Okay, alternating coefficient means cubic, to the power 2, to the power 1 and to the power 0. If their alternate coefficient is sum of alternate coefficients are equal, then we write a d which is equal to minus 1 is one of the root. If sum of all coefficients are 0, then we write d which is equal to 1 of the root. Or if a constant term absent, then we write 0 as one of the root. Okay, these are the 3 rules that we apply for synthetic division, and we convert cubic equation into the quadratic equation. Okay, so for finding the roots of a quadratic equation, it is easier for us. Okay, so we can see that here we write full form d cube minus d square plus 0 times d, as we don't have first power over here. Okay, that's why I'm writing 0 times d plus 2, which is equal to 0. All that process I explained already. Okay, but still need to understand. Okay, now see that sum of alternate coefficient cubic and this one and this one, see that are these equal or not? Okay, yes. So alternate coefficient means 1 plus 0, which is equal to minus 1 plus 2. So if you're going to add here, we get 1 which is equal to 1. Okay, that means sum of alternate coefficients, they are coming equal. This implies d which is equal to minus 1 is one of the root. Okay, d is equal to minus 1 is one of the root. So for finding the remaining roots using complementary function, it is easier. Okay, yes. So let me write here using the synthetic division. Okay, we take d is equal to minus 1 over here. I explained this method, but still I am explaining. Okay, yes, 1 take all the coefficient over here. Okay, d cube has a coefficient 1, d square has a coefficient minus 1, d has a coefficient 0, and it is remaining 2 over here. Okay, yes, these are the coefficient I written over here. Now see that we don't have any element here to commute with 1, so take 1 as it is down here, multiply these two element, minus 1 into 1, which is a minus 1, add both of them, minus 1 plus minus 1. Okay, so minus 1 we write minus 2. Okay, again multiply these two, minus 1 into minus 2, which is a plus 2. So add both of them, we write a 0 plus 2, which is a 2. Again multiply them, so minus 2, minus 1 into 2, minus 2, add both of them, you will get the 0. Okay, last step, it is here 0. So give first element for the power of 2, second element power of 1, and last element power of 0. That means we write a d square minus 2d plus 2, which is equal to 0, is a required quadratic equation. Okay, for finding the factor of quadratic equation, you have to apply a result. Which result we applying for finding the root, or for this quadratic equation, minus b plus minus b square minus 4ac upon twice of a. Put all these value, find out the factor over here. Okay, it's way easier. It's nothing we have anything difficult. Okay, it's everything easier. Now we have to put these values here and you will get the factor as I have found already. So 1 plus minus iota is another root. Okay, d which is equal to -1 and another root is a 1 plus minus iota. It is one remaining root over here. Okay, yes, so you put this value, you will get the complex root over here. Okay, yes. Now let's write the complementary function, as I don't have space but still I'm writing over here complementary function. So e to the power m1x, that means e to the power minus x. Okay, m1x means first root. We have, it is other than these two root, we have a different root as a -1, and this one is a complex root. So we apply one formula for here and another formula for here. Okay, yes, e to the power m1x, that means e to the power minus x. Now apply the result where we apply whenever we have complex roots. Okay, so what is the result? E raised to ax, that means e raised to 1 into x. Okay, e raised to a which is equal to 1 and b which is equal to 1. Okay, e raised to 1x, c1 cos bx, b which is also 1, c1 cos x plus c2 sin x. Okay, c1 sin c2 sin bx, b which is a 1 here. This one is our required complementary function. Okay, yes. Now we have to work for a particular integral. It is way easier than complementary function. Okay, let's get start our particular integral over here. So for finding particular integral, we know that particular integral can be found by 1 upon f of d into phi of x. Okay, so replace all these values here. So we know we have f of d as a d cube minus d square plus 2. Okay, that we already reduce our linear differential equation. Okay, yes, so we write 1 upon d cube minus d square plus 2. Okay, this one is our f of d. Already we found how, already I explained in my past previous part. Okay, that how can we get that d cube minus d square plus 2. Okay, this one is upon f of d into phi of x. Phi of x means which is the right hand side, that means e raised to z plus 1 upon e raised to z, that means we write e raised to minus z. Okay, so the next step, take this e raised to z with that term. Okay, e raised to minus z with this one, that means multiply this term under bracket here. So we are going to write 1 upon d cube minus d square plus 2 into e raised to z. Okay, plus keep as it is, multiply this one to e raised to minus z also, as we have standard form for finding their particular integral. Okay, so 1 upon d cube minus d square plus 2. Okay, d cube minus d square plus 2 into e raised to minus z. Okay, so these are the two terms I written this way. Okay, as we know that e raised to ax can be written as a as a d. Okay, that means we replace the value for a as a 1 here in the form of a d, here also a. Okay, again e raised to minus x. Okay, whenever we have e raised to minus x, then we replace these values. Okay, so you must have to check these videos in my previous playlist. Okay, I explained to you all how we can apply, how one can apply this standard form for finding the particular integral. Okay, so what do? We replace the e raised to ax, a which is equal to 1 here, that means e raised to az, replace a which is equal to 1 here and replace az, minus az it is there, so replace a which is equal to minus 1 here. So 1 upon 1 cube minus 1 square plus 2. Okay, so how I have replaced this one, let me explain one more time. Okay, e raised to az, the coefficient of that z we replace instead of a d. Okay, so a which is equal to 1, so 1 cube minus 1 square plus 2 into e raised to z, plus again we have minus az, that means coefficient of z which is a minus 1. Okay, then reply here instead of d as a minus 1, minus 1 cube minus of minus 1 square plus 2. Okay, be careful about their signs. Okay, sign convention, these are very much crucial here. Yes, so we write 1 upon 1 cube minus 1 square. 1 cube it is remain 1, 1 square it remain 1, 1 minus 1 it goes to 0, so we write 1 by 2 e raised to z. Okay, plus minus 1 cube it goes to minus 1, minus 1, and again we write see that 2 and minus 1 cube it is minus 1, so it is a minus 1. Let me write here minus 1 cube minus 1, minus 1 square which is a 1, so minus of 1 and plus 2. Okay, so minus 1 minus 1 minus 2 plus 2, it goes to 0. So whenever we have denominator 1 upon 0 e raised to minus z na, then that condition we multiply z to the numerator and take differentiation of a denominator. Okay, yes, so multiply z to the numerator, z into 1. Okay, as we have denominator goes to 0, that's why we are applying second condition from the result. Okay, yes, so z into 1 upon take the differentiation d cube with respect to d, so we write 3d square. Okay, and minus d square has differentiation minus 2d. Okay, constant 2, it goes to 0 and multiplied by e raised to minus z. Now replace again minus 1 over here. Now check it out, okay, whether it goes to 0 or not. Okay, so let's go for the next step. We write 1 upon z e raised to z plus z into 1, keep z as it is, and replace minus 1, 3 into minus 1 square, it remains 3, minus 2 into minus 1 plus 2. Okay, and e raised to minus z. Obviously we don't have denominator 0 over here. Okay, so we can define the quantity here as e raised to z upon z. Okay, it is not the z, it is a 2, it is 2 here from e raised to z upon 2. Okay, e raised to z upon 2 plus, okay, e raised to z upon 2 plus 3 z e raised to minus z, z e raised to minus z, okay, upon 3 plus 2, 5. Okay, this one is the our required step here. Okay, yes. So as we have right hand side, which is a 10 into x plus 1 by x. Okay, so it is a 10, that term it is still remaining here. Okay, that means that term it is here with the e raised to z plus e raised to minus z. Okay, 10 it is here. Okay, 10 it is a constant, so taken out here. Again 10 constant, that taken out here. Again 10 constant, taken out here. 10 out here. Again 10 out here. Okay, yes. So I hope you all have understood how that 10 it is there. Okay, because it is the right hand side of our given example. Okay, so 10 it is there. So how can we write next step? So 10 into e raised to z by 2. Okay, 10 into e raised to z by 2. Multiply 10 under bracket 10 into e raised to z by 2. That means 5 e raised to z. Okay, plus 10 multiply over here, 10 by 5 means 2 e raised to minus z and multiplied by again z. Okay, this one is our required particular integral. Now see guys how easy solution it is, but just you need to understand what are the actual format, what are the main steps. Okay, which is the formula, which is the result we have to apply for specific example. You need to identify which type of the examples are these. Okay, see guys, this type of the examples are coming for 4 to 5 marks. Okay, in your SPPU question paper. I don't want to miss these questions. Okay, from you all. Okay, I want you all to prepare these questions. These are very easy question, gives us the easy mark. Okay, this one is a particular integral. As we have found the complementary function, then put it here, particular integral, put it here. Okay, then we get the complete solution. Which is a complementary function plus particular integral here. Okay, this one is our complete solution. So I hope you will have understood my first example, which based on the Cauchy homogeneous linear differential equation. Okay, so Cauchy homogeneous differential equation. First we reduce that Cauchy homogeneous differential equation into the linear differential equation, and then we apply straightforward process that we learned in previous lectures. Okay, yes, I hope you all have understood my today's lecture. So even after, if you found anything difficult na guys, let me know in my comment section. I will come up with the similar videos. So thank you everyone, thank you for my today's lecture.